Hi, so we're beginning Unit 5, Chemical Kinetics, and this matches right up with the textbook chapter 14. So even if you haven't been using the textbook much so far this year, this may be the time to pull that out and follow along. All the graphics, all the example problems, all the homework problems come right from that textbook. So it's another resource that you can use. The first learning objective is just an overview of reaction rates and what are some of the factors that can influence the rate of a reaction. And in first year chemistry and in previous science classes, you may have talked about some of these factors that can influence the rate of a reaction. If I was asking you to dissolve some sugar in water and how could you speed that up, oftentimes you would come up with, well, you could increase the temperature, you could stir it. Someone might say that, oh yeah, if it was a sugar cube, it would take longer to dissolve than just granulated sugar. And those reactions, or that is just a physical change, it's not necessarily a chemical reaction, but the principles are all the same there. An additional one that might be new to us this year, now that we start thinking about chemical reactions happening in aqueous solution, so having a concentration or a molarity associated with the reactants and products, concentration is another big piece, another factor that can influence the rate of a reaction. And what do all those four factors have in common is that they increase the number of collisions, and as we're going to see a little later on, they increase the number of successful collisions. One thing that's not included in that is a catalyst, and catalysts definitely speed up a reaction. We'll talk more about how that happens in the very last video in this chapter. So now let's start talking about how we're actually going to quantify the rate of a reaction rather than like it's slow, fast. How do we get a number associated with it? So the number that we would associate with the rate of a reaction is a change in a concentration, could be reactant, could be product, over a change in time. So if I look at this graphic and look at how concentration may change over time, what is the rate of appearance of B? So whenever we look at a change is always going to be final minus initial. So what's final B is 0.7. What was the initial 0? So 0.7 minus 0. We would say 0.7 moles over the change in time. Look at the little time stamp on it. We would see that it says 40 seconds. That's the change in the appearance of B over time. What is the rate of the disappearance of A? So the fact that it says disappearance tells you we're looking for a positive number. It's not saying the rate of change of A, because the rate of change, look at above the word change there, final minus initial. If I look at A, what's going on with A? Well, if I did final minus initial, I would get 0.7. Or negative 0.7. And the fact that it's saying disappearance is where it's saying like we don't need the negative. We know it's going down. So we would do the same thing, right? It changes by 0.7 mole over that same 40 seconds. And I'm just showing you this to illustrate that by convention, by definition, we have decided as chemists that we're going to say the change in the concentration or the rate of a reaction is going to be positive. So how does the rate change with time? We will talk a little bit more about this because it is going to involve some calculus that we don't need to do, but it is more advanced math. But if you just look at the data from this chemical reaction, C4H9Cl, the name for that would be chlorobutane. So chlorobutane reacts with water to produce butanol plus hydrochloric acid, HCl. What happens to the rate as time goes on? And it's pretty easy to see what happens. The rate goes down. Why would the rate go down? Well, the rate's going to go down because one of those four factors that we put on that first page changes, and that's the concentration of the reactant. Remember that C4H9Cl is a reactant. As time goes on, the concentration of that decreases, therefore the rate decreases. So we would say the rate decreases because the concentration of the reactant or reactants decrease. That means that there's less collisions, therefore the reaction slows down. Another graphical view of this would be looking at this graph that shows on the y-axis the concentration of the reactant over time. And if we were looking at the slope of that, right? Think of what slope is. Slope is change in y over change in x. Change in concentration over change in time, which is rate. So the slope of that curve would be analogous to the rate. And we would see that, look at the yellow line, the slope is fairly steep, and then the blue, it's a little bit less steep, it's smaller. How do you find the slope of a curve? Well, that is calculus. That's called taking the derivative, and it's actually pretty simple. Once you know calculus, and if we knew the equation for that line, that's not something you're going to need to do in AP chemistry. You just need to understand that the instantaneous rate is the rate at a particular time and that it slows down as the reaction goes on. So, reaction rate and stoichiometry. On that first picture of the red and blue circles of A and B, they were the same. That A disappeared at the same rate as B appeared, and that will happen many times if the coefficients of those chemicals are the same. So if we look at that reaction with the chlorobutane, one molecule of chlorobutane will decompose, will react at the same rate that the butanol is produced, because one needs to be used up to make one of the other one. So they would be equal to each other. But what if the stoichiometry is not the same? And if I look at this molecule, really think about what is going on, right? So we would say 2 HI have to disappear to make 1 I2. So what is the rate of those? Well, I2 has a certain rate. HI would disappear at twice the speed, right? Because it would take 2 molecules of that. So we can see that definitely rate is proportional or is related to the coefficients. So another way to think about this is the rate of the HI. We said the rate of the HI disappearing is twice as fast, or we could say the rate of the H2 is 1/2 the rate of the HI disappearing. And that's actually the formula that we would use for this. So in general, we have a kind of looks crazy, so just write it down and then we'll use it a few times so you can understand. So what is this saying? This is just like the other guys are related, just like we said here. The rate of the H2 is 1/2 the rate of the HI. We take that rate and it's 1 over the coefficient of that. So what is the rate of the change in D? Well, it would be, 1 over the coefficient of A times the rate of A. We can see these guys are negative here. Why? Because if we're doing change in concentration, change of the reactants would be negative. So we have a negative sign in front of that to make it positive, because we always think of those in terms of positive numbers. So an actual example here with this reaction, this is actually the decomposition of ozone. And we would say that if you take the change in the rate of ozone is O3, by the way. If I take and multiply that number by 1/2, it would be 1/3 the change in the concentration of oxygen gas. That's me applying that formula on the previous screen. And then actually using that in a problem here, right? If the rate at which O2 appears, remember we're still going to circle the do, underline the clue, is 6.0 times 10 to the -5 molarity per second. At this particular instant, what is the rate of O3 disappearing, which is negative delta O3 over delta T. So we know we have 1/2 right? This is me applying that, just rewriting basically that formula. Thinking about what do I want to solve for? Well, I want to solve for negative delta O3 over delta T. So how do I isolate that? Well, pretty easy. I just multiply both sides by 2, right? So negative delta O3 over delta T equals 2 times 1/3, 2/3, and then substitute in 6.0 times 10 to the negative 5 molarity per second, or 2/3 of 6 is 4. And that's often, by the way, molarity per second. That's a very common way of talking about the rate of a reaction. Change in concentration, molarity over change in time. Here's a multiple choice question, very similar. A certain time in a reaction, substance A is disappearing at a rate of 4 times 10 to the negative 2 molarity per second. So this is A. Actually, I will highlight it. Substance B is appearing at a rate of 2.0 times 10 to the negative 2 molarity per second, and substance C is 6.0 times 10 to the negative 2 molarity per second. So now think about what does that mean for the coefficients. If B is 2 and A is twice that, that must mean the coefficient of A is going to be 2. Coefficient of B would be 1, coefficient of C would be 3. So now I sort of know the coefficients of these. Which of the following could be the stoichiometry for the reaction? So I look at the reaction where A is 2, B is 1, and C is 3. And I get that it could be A or C. So now I look a little bit more, and if I look, I see that B is appearing at a rate of 2.0. So what does that mean? That means B must be a product. And so that's how I can figure out that the right answer there is C. Another practice problem is talking about dinitrogen pentoxide reacting or decomposing to produce 4 nitrogen dioxide molecules in oxygen gas. At a particular instant, the N2O5 is 4.2 times 10 to the negative 7. I want to know the rates of the other species. So A is NO2. Apply that same formula. 1 over 2, that change in the concentration of N2O5 over delta T. Think about what I want to solve for. I want to solve for this. How would I get that all, how would I isolate that? I'd multiply both sides by 4. So 2 times 4.2 times 10 to the negative 7 molarity per second, or 8.4 times 10 to the negative 7 molarity per second equals the change in the concentration of NO2 over the change in time. Same thing for B. B is looking at O2. So 1/2 This is what I want to solve for. Pretty straightforward. I'm just going to multiply the 1/2 times 4.2 times 10 to the negative 7 molarity per second, which would equal 2.1 times 10 to the negative 7 molarity per second. Both of those I was able to solve without a calculator. Means it would be perfectly appropriate for an open response or multiple choice question.